This is an NSF center, so thank you for your hard work. Hopefully this will generate enough excitement that there will be students next year to follow in your path. I also want to thank Sunu and Sarah, who you met out there when you came in to register here. Thank you. Who basically put together all the logistics for you, finding you a place to sleep if you're from out of town, and making sure that you get fed for 3-4 days. So have a good time, and you should really hassle the speakers. That's my advice to you. Welcome.
Thanks, Ali, for the welcoming speech. Before the lecture starts, I have some administrative announcement. So here is the lecture hall. We will have our lectures here. You have Wi-Fi access. The PU visitor is open, and you can also use the EduRoam. And the restroom is near the main elevator. It's about over there. You will find it. You won't miss it. And the information about the maps, and you can pick up your name badge outside. Please make sure everyone wear the name badge all the time during the summer school. And yes, that's almost the stuff. And also, in case you need some receipt of the participation and attestation of the participation. Yeah, it's available in the badge, so you can double check that. If you have further questions, please come to us or come to Suno or Sarah at behind. Okay, any more questions? Okay, good. Now I guess it's a good time to start our first lecture. Our first lecture will be given by Gil. Gil got his bachelor degree in math and physics from University of Tel Aviv, and he graduated from Harvard and got his PhD there. And now he is a professor at Caltech. Gil has been interested in many aspects of condensed matter theory. Today he will bring us some story about the topological effects in the driven quantum system. Let's welcome our first lecturer.
Thank you. It's really fun to be here. I have to say that ever since I was an undergraduate, I dreaded like 9 o'clock classes. It was true when I was a student, and it became even more true when I became a professor. So don't just harass me, help me out. Try to remember what I'm supposed to tell you at this early hour of the morning. Okay, so we figure out the boards and then we can start. So first of all, do you prefer Blackboard or PowerPoint? Blackboard? Okay, good. Don't worry, I will have some PowerPoint for you later on. Just in case, just in case you feel like information deprived. Thanks. This helps? So what I want to talk about is the combination of topics between dynamical quantum systems and topological physics. And my idea is that, and this guided my work in the past couple of years, that when you combine insights that we have from topological physics in solid-state systems with intuition from driven systems and apply topological principles to driven systems, light-matter interacting systems, you can get new ways of controlling both light and matter. So topic is topological phenomena. In quantum dynamical systems. And let's see, I actually prepared a bunch of topics. I don't know if I can run through all of them. The problem with a topic like this is that I need to both tell you about topology and about dynamics, and then about the combination. So I have to do all this in 2 classes. And I wanted to start maybe with topology. Is the microphone on? No. There you go. Wasn't that loud enough? I mean, yeah. Is this better?
Yeah. Yeah, it's also for
It's recording?
Yeah.
Okay. So, right. So the first thing, how about like this? Can you read it in playwright like this? Okay, so let's start with topological systems, topological models. And I want to talk about two. So Majorana fermions in Kitaev chains. And the second example would be the Bernoulli-Hughes-Chang model for quantum anomalous Hall effect. Now, I take it that some of you are familiar with both of these models, but are all of you familiar completely with both of these models, or should I run through them a little bit? Run through them? Is that okay? If you get bored, like start yawning. I'll count the yawns and then I'll move forward. So this will be the topological introduction. And then I'll need to give you a dynamics introduction. And you know, I'm a little biased given my career path. When I talk about dynamics, it usually somehow managed to make its way into Floquet physics. So I'll talk a little bit about Floquet Hamiltonians, Floquet problems, and by which I mean time periodic modulations of a Hamiltonian. And we'll look at two examples, or two limits. Weak driving and strong driving. And then, finally, I think sometime before the end of the day, we'll combine the two to get to consider two dynamical effects that arise from topological physics. The simplest one would be, I don't know which is the simplest one. The first one would be Majorana multiplexing. And the second one would be topological frequency pumping. It may sound mysterious, and because it sounds mysterious, it means that it's hard to draw on the board, so those will be the parts that we'll do with PowerPoint. But by Majorana multiplexing, the idea is that we'll talk about Majorana chains, how you get Majorana fermions at the edge of quantum wires. We'll talk about how you get anomalous quantum Hall effect in two-dimensional electron systems. But what I'll show you is that with the chains, if you irradiate the wire with multiple frequency, you can actually produce you can produce many more Majorana fermions in the wire that are associated with the different frequencies and the different drives. And likewise, we will use the Bernoulli-Hughes-Chang model applied to a single spin driven by two light beams, and the spin will become a converter that will take energy from one light beam and put it in the other one. And that would be an exact analogy with this model, but could have applications in terms of converting one laser into a beam at a different frequency, but maybe we don't have such good control, etc. So it would be a way of controlling light fields. All right, so should we start? Should I start with, I can start either with this or with that. Any preference? As is? All right. Yeah, this is a little more formal, so maybe it's good to start with this, and then when you hit your like 10 o'clock low, we get there. Okay, so topological models. Let's start with Majoranas. For some reason or another, Majorana has become kind of a holy grail. Everybody wants to have Majoranas in the lab. Theorists love talking about Majoranas. A big chunk of it is topological quantum computing. So Alexei Kitaev, in I think 2001 and a little before even, pointed out that if you have nanobillion anyons, they can encode quantum information non-locally. So the idea is that, and I won't talk about it too much, but I'll just remind you, if you have like two Majorana fermions, they actually give rise to a single fermionic state, but it's encoded non-locally. And then you can braid them and fuse them, and by doing so, you can actually carry out all, essentially all quantum information gates on such on a qubit, which consists of, say, the parity that's encoded in these two Majoranas. Now, how many of you understood what I just said? Not so many. Good. So that's what we need to talk about. What do I mean by Majoranas? I won't talk about their braiding, but I can give you some notes later on if you're interested about braiding. But really the idea is that Majoranas give rise to degeneracy in the ground state of this system that can encode quantum information, but it encodes it in the entire system. And that sounds mysterious, sounds weird, and that's why a lot of people really wanted to realize those things. And so far, I think Leo Kovenhaven managed in quantum wires, Moti Heiblum as well. Ali was here. See around? Ali has Majoranas in his lab, in the iron chains deposited on lead superconductors. Okay, so let's start. So what are Majoranas? So let's start with a simpler thing than Majorana. Let's start with a Hamiltonian that looks like this. Single fermionic state, right? Has energy mu. So it has two configurations. It can be full. Let's call it 1. And the energy would be mu for this, right? It could be empty. And then the energy would be 0. And we know that we can connect the two states like this, right? Why am I starting with this? Because this system has actually two Majorana fermions in it. Nothing stops me from defining an operator that looks like this, gamma plus, and also gamma minus. I can do that, right? I just did. Gamma plus dagger is what? Self, gamma plus. Actually, that's true also for gamma minus. So both of these operators are real. They're the conjugates of themselves. What is gamma plus or minus squared? 1. Because it's C dagger C plus CC dagger. That's just anti-commutation. And the anti-commute. So gamma plus gamma minus is minus gamma plus. So there you go. You have a single state. If you really want to imagine it as a state, let's think of it as something that's, some state that's bound to some potential. Then you know that there will be some localized state, right? And this could be like the second quantized description of this wave function, of this bound state. So there you go. We have not just one Majorana, but we have two. What's the problem with those two Majoranas? Can I use them for anything? Why?
Not spatially separated.
They're not spatially separated. Very good. They're in the same place. They're the same wave function. They don't help with anything. It's just an equivalent description of this simple system, which we all analyzed, I don't know, second or third year of our undergraduate, right? So the question of how to separate Majoranas. Now, I have to apologize, but sometimes I write Majorana with a big M, sometimes with a small m. It is a person, so in principle it should be big M, but we use it so much that maybe you can use lowercase every once in a while. So to separate those Majoranas, you really need some kind of a magic trick. And back in the day before liability claims, etc., in magic shows, I think there used to be this magic trick where magicians would take a volunteer from the audience, put them in a box, and then sew the box in two, and then separate it, and then somehow bring it back together, and the person comes out and it's fine. So when I give PowerPoint presentations about this, I try to get a picture of this magic trick, and not surprisingly, the only pictures that I could get were in black and white. So it's a lost art. But we really need to do the same thing here. So if we want to separate Majoranas from each other, let's start with two sites. and figure out maybe how that works. So notice that I'm using square for sites. And the only reason why I do this is because there are a lot of zeros running around. So I don't want us to be confused between the zeros and the sites. Okay, so let's think about two sites. With Hamiltonian that has, say, a chemical potential. Let me put a minus because I'm just used to putting minuses in front of chemical potentials. By the way, are you all comfortable with second quantized notation? Really ask me questions. Like I don't have to cover everything. So let's have a chemical potential. You can think about it as a gate that's applied to every site. And what else can we have in this Hamiltonian? I can couple them. I can do hopping, right? Let me do this. For good or for bad, I am obsessed with Majoranas, and therefore I want to describe these two sites with Majorana fermions. I can, right? I have the mapping over there. Let me just stick it into this Hamiltonian and see what we get in terms of Majoranas. So the first thing is the number. Let me work out what this C dagger C is separately, very quickly. So C dagger C for 1 or 2, let's see what it would be. Actually, do you have a guess what it could be? Speak up.
Gamma plus times gamma minus.
Gamma plus times gamma minus. That works. Can it be just this? There could be a minus sign, but there's a bigger problem with this. I. It's anti-emission. So let's turn it into an emission thing. Now it has to be something like this because everything else is either 1 or 0, right? Gamma plus squared is 1. Gamma minus squared is 1, right? The anticommutator is 0. That's the only thing that remains. Let's just make sure that this is correct in terms of the sign. So, in fact, this would end up being either +1 or -1, right? So let's add a 1 and divide by 2. And now let's just make sure that the signs are correct. I think it's okay, right? So C plus, oh, oops. I'm telling you, it's early in the morning. There you go, right? C dagger squared is what? 0. CC is also 0. And then we have C dagger C with a minus, but that's nice because we have 2 i's, so everything cancels. And we have another CC dagger with a minus. So again, it becomes C dagger C with a half. And trust me, the half will get cancelled because of the anti-commutation. Okay, so this is true, right? Now, with that in mind, can I erase this middle step? Great, just I'm a little OCD when it comes to the blackboard. Okay, then I can take this Hamiltonian and start with minus mu times I gamma 1 plus, gamma 1 minus. You understand the notation, right? Site 1, site 2. How many of you are bothered by the fact that I'm not starting with site 0 and site 1? I see some C programmers in the audience. Python also has that power, right? But in Mathematica, it's okay. Okay, so this is this piece. And yes, I dropped a constant. This is the time to give you a disclaimer. I'll drop constants occasionally. Sometimes minuses will turn into pluses by mistake. But you know, with Majoranas, nobody knows whether it should be a plus or a minus to begin with. So it doesn't really matter. So don't quote me on this too much. I know I'm on tape, but
I'll try to be honest with my minus signs, but keep an eye out. Now, what about this? This we need to work out a little bit, right? So to be efficient, I'll note that this and that are emission conjugates of each other. So let's just do one of them. Okay, so C1 dagger is C1 plus. Sorry, it's gamma 1 plus gamma 1 minus over 2. Take a quick look to the left and see if you agree with that statement. Is that okay? Here's a more complicated one. Oh, wait. I. Yes. But it's minus I, right? Yeah. Minus I. Thank you. I's go under my previous disclaimer as well. And then gamma 2 plus I, gamma 2 minus. Do you agree with that statement? Is that right? It's okay? Okay, now we have to open up these brackets. Tell me something. Gamma 1 plus, gamma 2 plus. It will have a partner here, which is gamma 2 plus, gamma 1 plus, right? What would be the sum? 0, because all of the Majorana fermions anti-commute with each other. Similarly, gamma 1 minus, gamma 2 minus will be 0, because there's no I in front of it. But everything that has an I can stay. And then we end up with 1/2, I think, I gamma 2 plus gamma 1 minus plus I gamma 1 minus gamma 2 plus. And I think I took care of the emission conjugates by eliminating one of the halves. Why did I do this? I did it because I wanted to get Majoranas that are separated from each other, right? Now, right now what I have is I have the mu giving me a connection like this between the Majoranas on a single site, right? And then I get two more connections that look like this, right? Now, what do we mean by a connection like that? Every time that you have two Majoranas that are connected, yeah?
I think one of the subscripts might be off on the gammas, because right now they'll just cancel, right?
Oh, oops. Gamma 1 plus, gamma 2 minus. You're great, thanks. Yes. Yeah, and gamma 2 plus is this one, gamma 1 minus. And then we have gamma 1 plus to gamma 2 minus. Is that right? Now, every time that we have a bond like this, right, it's like the two Majoranas form together a single site that can either be either full or empty. Right? This is something that we need to be comfortable with. Two Majoranas give rise to a single regular fermionic state. It's either full or empty. So you can say that two Majoranas can have like either even or odd parity. Right? Even parity, odd parity. All right. But I still want separate Majoranas. So what should I do? Let me make it even simpler. Let's get rid of the mu. Let's set mu to 0 for a bit. What else should I do? It's a little suggestive.
Get rid of the top line.
Get rid of the top line, yes. Suppose I get rid of the top line. It's not clear I can do this in this Hamiltonian. Okay, I have both in terms of J, right? But if I manage to get rid of the top line, I have these two Majoranas giving rise to a single state. Nothing unusual in that. But what happens with these Majoranas? They'll be free. And what do I mean by free? So if we take out, we said this one, right? If we take out this one, we find that the commutator of H with gamma minus and the commutator of H with gamma 2 plus is what? 0. Which means that when you apply gamma 1 minus to some eigenstate of this Hamiltonian, you'll get a different eigenstate with the same energy, right? So it's like a quasi-particle that does not change the energy of the system, right? Same here. And we have two of these free guys, right? So both of them can still have odd or even parity, full or empty. Except where is this full or empty? In the two sides of the system, right? This doesn't look so impressive because it's just two sides. They're very close to each other. So Alexei Kitaev said, hang on a sec. This is too good. Let's just make more of it. Let's turn this into a sum over all sides and all bonds. So I'm doing a little bit of blackboard algebra. And just to make it a little harder on myself, let me just copy from the bottom. Minus j over 2 times I times gamma n plus 1 minus. Now I can erase this. Is it okay if I erase this? What do I have now? If I do this, then we form a chain. Each side can have a chemical potential, and all sides have it. Each sides look like a European electrical socket with the plus and minus Majoranas. And we have bonds that look like this, like a single chain. And what do we have left? Two free Majoranas, right? So this is due to Kitaev. And this is the thing that got started, the idea that maybe you can get Majorana fermions as quasi-particles in solid-state systems. Yeah?
I think I missed why you got to just drop that last bond.
Yeah, I skipped a step. So you need to go back and say what that step is, right?
Yeah.
By the way, when you ask questions, just to raise the ante, can you tell me your names? I'll start maybe remembering some. So
I'm Michael.
Michael, thanks. And I'll enforce it henceforth. But if you don't feel comfortable, just answer me when I ask you what your name is. No, answer. Please answer. Okay, yeah. So this Hamiltonian is not the same Hamiltonian as what I advocated before, right? What should we do?
Add more sites and couple them.
Yeah, so, well, we have the sites, but I just don't know how to make the single bond and not both bonds, right? Let's do backwards engineering. This is the Hamiltonian we want. What we want to do is, so maybe we should substitute for the gammas, right, the operators that they mark and see what we end up with in terms of electrons. And let's do that. But so far, I wanted to convince you that this is a way of getting free Majoranas on the two sides of the chain. You happy with that? This is actually quite an amazing feat because, you know, the chain, as it is, you know, what is it? It's some model, right? This model is particle Hall symmetric, so we'll draw dispersions in a little bit, and you find out that there's like a positive part and a negative part. They look the same, right? But then on top of this usual dispersion, I'll just draw it now and I'll derive it in a second. By the way, can you see this part of the board? No, you guys probably not. So let me go back here. Actually, I'll do something else. Right, so there'll be some dispersion like this, right? But on top of that, there are two extra excitations gamma 1 minus and gamma n plus. Right? I don't know where to put them. They don't really have a momentum. They're on the edge. Let's put them here, like at 0 energy and at 0 momentum. Well, that's the closest approach. There are two of them, right? And they give rise to a state that can either be full or empty, right? And by full or empty, we know that we can write this. But it's like taking an electron and saying, well, it's here. Right? It's here and here. Now, you're used to it in the sense that you're used to having electrons with wave functions that are, I don't know, in double well potential. They're like probability half here and probability half here, right? This is not that. This is something much worse. Because if you have like a double well potential, right? And you want to ask, do I have an electron in the double well or not? What will you do? You measure whether you have an electron in one of the wells, right? And then with some probability you'll get 1, some probability you'll get 0, but you'll always get 0 if there is no electron, right? Now if you try to measure the density of electrons here, right? It always give you, I mean, it will be uncorrelated with this thing. Why? Because you need both Majoranas, the one here and the one here, to create the electron. So there's no local measurement that can discover what this parity is. There's no local measurement that's correlated with what this parity is. This information is stored in the entire chain. Likewise, if you want to create this, if you want to move between the even and odd parity sectors, I don't want to talk about it too much, but if you're curious, I wanted to write these things down. You can define the C dagger to be gamma 1 minus plus I, let's say minus gamma n plus. And likewise, the emission conjugate, right? But you see, you're creating it in both locations at the same time. Now, there's another argument for the double well analog. If you had a double well, how many fermionic states you would have bound in this double well? Imagine having like a double well, two negative delta function potentials. Each one has a bound state associated with it. How many bound states do you really have? 2. Symmetric and antisymmetric, right? Either one of these can be either empty or full, right? How much Hilbert space? Each well has Hilbert space of dimension 2, right? So the Hilbert space size is 2 squared. How much Hilbert space is associated with each one of these Majoranas? What? Square root of 2. Say your name?
Rishi.
Rishi. Rishi is saying square root of 2. Let's see. Square root of 2 times square root of 2 is 2, which is indeed true because it can be either full or empty. So that should give you an idea of how strange it is to have Majoranas that are separate from each other. Now, every time that you have a particle with a fractional Hilbert space, that means that when you braid that particle with another one of its kind, you'll get some non-trivial result. In this case, braiding two Majoranas would give you a minus sign if, will give you an I if you get, if you're in the +1 case, and a minus I if you're in the -1 case. And this is how you can start making, gates of these Majoranas. But it's not the topic of my talk. So if you're interested in this, ask me over lunch. I'll be happy to provide you notes. Questions so far?
Is this like a precise thing to be saying, though, that like Majoranas have like square root 2, or is it just some like, heuristic?
No, it's a very good question. Name?
Alan.
Alan, thanks Alan for the question. It's a very good question. So it doesn't make sense to talk about a single Majorana and say that it has square root of 2 because every system that has a single Majorana will have another Majorana somewhere. And likewise, for every non-abelian nanion, like say Fibonacci particle, etc., you cannot see them just as single particles. But the idea is that if you look at a large system with a lot of them, in the limit of large number, when you ask what's the Hilbert space, is that fractional number to the power of the number of quasi-particles. So in this case, it's kind of easy to digest because every two of them make a reasonable Hilbert space. But Fibonacci anyons, it's not. It's like the magic, the golden mean to the power of the number of particles. It's never an integer. So it's a statement about the, if you want to ask what's the dimension per particle for a large particle system, for a large number of particles, then that's the limit. But Hilbert spaces should always be integer sized. So it would usually be the floor of whatever the dimension is, the power of the number of particles. So in that case, like if you have like a single Majorana, square root of 2 is like 1.4 something, the floor of that is 1, which is comforting. There's at least one state in the Hilbert space. But you can see how, yeah, right. So you have a single fermionic state can either be full or empty, delocalized between these two sites. Right. How do we do this? So this is how we do this on paper. How do we do this in practice? So we need to work back and see what this means. We know what this means, right? This is chemical potential. Let's figure out what this means. So let me just work it out for a single bond. This is the term that I need to work out, right? Can you all see my handwriting okay in the back? I hate to say this, but I always got C for handwriting back in school. It's traumatized me for life. Wasn't Hebrew though. I mean, it's more curvy. Let's see. Okay, gamma n plus, that's Cn dagger plus Cn, right? Gamma n plus 1 minus is Cn dagger minus Cn plus 1 times I, right? So the time I, I'll write it here. There's room. I don't need any halves, right? I and the minus will cancel. What do I get? Okay, on the one hand, I get Cn dagger, Cn plus 1. We love those. This comes with a minus sign. We also have its omission conjugate, Cn plus 1, Cn plus 1 dagger. So plus its omission conjugate. What is that? That's just stopping, right? That's what we had before. Now we have an extra piece though. Cn dagger, Cn plus 1 dagger. And its omission conjugate. What is this thing? C dagger. What is that? Superconductivity. This is sparing. So it seems like we can do this if we know how to take the system. Notice that it's spinless electrons. But I can tell you some other time how to get the spinless electrons. So let's assume that we can do this for spinless electrons. So it implies that what we need is some superconductor that will give you electrons in pairs, right? And produce proximity between sites. That will produce proximity. Now, because we only have one electronic state per site, right? We cannot put 2 electrons into a single site. We have to split them between nearest neighbors. So what this implies is pairing or proximity. Which pairing? I heard something good. P-wave. What's your name?
Shane.
Shane. Shane?
Shane.
Shane. Shane is saying P-wave. Why P-wave?
Because you have some spatial difference between the two pairs.
So there's spatial difference between the two pairs. That's right. That's going to come in. Could it be anything other than P-wave?
Fermion statistics.
It's fermions without spin, right? So it cannot be S-wave. It's a bit of a trick question because it probably can be, but then we need to start remembering what comes after S and P. So S, P, D, F, right, etc. So it can be F too, because that would also be odd pairing. But it can only be odd pairing, cannot be S-wave. You may wonder, how do I get a P-wave superconductor? People are working on it. But actually, the answer is that to get this model, you need a S-wave superconductor and a proximity to a quantum wire that has spin-orbit coupling. And that does the trick. That's how Leo Kovanoven did it. Okay. So it seems good. So we can get those Majorana fermions with P-wave pairing. Now, this is a rather complicated way of writing this Hamiltonian. Let's just write it in terms of BDG Hamiltonian. And then I'll be done with the Kitai model. Now, I'm going through this relatively quickly, and I'm dropping a lot of hints about other things. So on the one hand, ask me questions. On the other hand, if you want to draw me into something else that interests you, ask. I can spend like a few minutes doing a tangent. So questions so far? Anything?
Can you elaborate on the comment on how to create one of these Majorana wires in the lab? Putting a
Sure. So having a chain of fermionic states, it's easy to think about it as going into a wire, right? Just a continuum limit. Now the problem with the wire is that it has both spin up electron and spin down electrons, right? And they have this quadratic dispersion. By the way, I need to be strict. So could you tell your name?
Tyler.
Tyler. So Tyler asking for the actual physical realization. Did I say I'm a theorist, by the way? So this would be the theorist perception. Like I heard Cam saying that this is the way the theorist, that this is what theorists think is a quantum wire. You just draw it and it's like in PowerPoint, you use the cylinder and you just stretch it out. That's, yeah, so you have these two, right? And then if you can put a superconductor coating which I think, if I'm not mistaken, it used to be niobium titanate, something like that. But I think now they use aluminum titanate, something like that, because it matches atomically very well to the material. But okay, so the story goes like this. So you put a superconductor in proximity. You assume that there's some chemical potential somewhere. It'll create proximity and it'll open a superconducting gap between those two sides. Bad, because it's still S-wave. And then the idea is to use a material that has strong spin-orbit coupling. So either indium antimonide or indium arsenide seem to do the work pretty well. And spin-orbit coupling does the following thing. It splits the spins depending on your direction of motion. So what it does to this dispersion is do this. Because there's a term in the Hamiltonian that's momentum times sigma z. Then you have a combination of p squared over 2m plus spin-orbit coupling, which is a Rashba interaction, p times sigma z. It looks like this. Now you do another thing. You add a magnetic field perpendicular to the direction of the spin-orbit coupling. Now, this is going to create a gap. Let's assume chemical potential is around here, even though it doesn't really matter for where the gap is. This opens a gap. where does it open the gap? Which momentum? Should be where, what?
They cross.
Where they cross. Thanks. Mike, right? Yeah, Mike says where they cross. That's a very good intuition for anything that's not superconducting. It will create a gap where the curves cross. Now, if the chemical potential is over here at 0 energy, how many fermions do you have? 1. If you just forget about the fact that this came from a spin up and this came from a spin down, should have said it. This is the parabola for the spin down. This is the parabola for the spin up. Now you have a band that mixes the spins and another band that mixes the spins. And if you don't know anything about the spin, you would just say, well, no, I just have a single parabola, or parabola-like dispersion. I don't know about the spin, just single fermions. And now the pairing will produce pairing between this part of the Fermi surface and this part of the Fermi surface. That will be p-wave pairing. Now, how come the S-wave can induce p-wave pairing? It's because this is, even though this looks like a single fermion, right? Still, the electrons here point up mostly, and the electrons here point down mostly. So they can pick up the pairing between spin up and spin down electrons in the S-wave. There's just no partner of the down-up that usual S-wave superconductivity has. So that's the idea behind the experiments. Now the experiments themselves are miraculous because you take this wire, you put them, you coat them with some whatever, neoprene titanate, whatever it is, and you put a magnetic field. You put a tunneling tip near the edge, and you hope for the best. You hope to see some Majorana fermions popping up at 0 energy. And somehow they did, without knowing how many bands there are in the wire, without knowing whether the proximity would be good. You can imagine that the first experiments had tons of defects in the wire. It somehow worked. And that was Covenhoven experiment, and then that was an indium antimonide, and then Motte-Heilblum followed very quickly with indium arsenide. And it turns out the physics is a little more complicated than that, but that is most of the story. And then Ali has grains of iron that replace this. The iron is magnetic, so you can think about the iron giving itself the magnetic field. And then it sits on lead, which also has spin-orbit coupling. And is also superconducting. And it ends up being the same model. Pretty much. There are always details. Questions on that? No, this is not exhaustive, but this is giving you a flavor. Other questions so far? We're good on time. You can ask. Don't be shy. And stop me if I go too fast, or yawn if I'm too boring. Otherwise, I don't know. All right, so we were saying we have this Hamiltonian second quantized, and the header here, the title is Bogolyubov de Gen. Don't expect me to write Bogolyubov on the board. I'm not willing to commit to any spelling of that word. So the Bogolyubov de Gen version of the Kitaev model. Let's write that. Can I erase this? Anything fermionic and non-interacting, there's no real reason to use creation and annihilation operators. You can usually reduce it to some kind of a Pauli matrix statement, and that's not different here. So I can write this Hamiltonian. Actually, I misspaced my introduction. Let me first do a conversion. I want to write this Hamiltonian in terms of Pauli matrices, multiplying CK and CK dagger with each other. And by K, I mean momentum. But this is written in terms of single sites. So it's a small conversion table for how we go from there to momentum. So I have sum over n of Cn dagger Cn, right? I know how to convert this into momentum representation, right? It's just sum over all momenta, CK dagger CK. It's always good to have this formula in mind. square root of n will give you the right normalization. Okay, that's good. How about hopping? Should be something similar, right? So ck dagger comes from the cn dagger, and ck comes from the cn plus 1, right? But the plus 1 is going to roll into a plus 1 here, and we're going to have an e to the ik. We're going to have an e to minus ik from the emission conjugate, so we'll get the cosine k that we all love. And then there's a question about this baby. Plus its emission conjugate, right? A little scared to write the emission conjugate right away. It's like taking on more than I can chew, possibly. Let's see. So there will be a sum over k, right? Yep. Okay. But let me confine myself into positive k. And just write the k and minus k separately. Okay, so there will be a ck dagger from here, right? Now, will there be a ck dagger from here? Yeah, it better not be, because ck dagger squared is 0.
It'll be a different K.
It will be a different k. What other k do you think it could be? Minus k. It has to be minus k because it's like e to the ik from here will cancel the e to the minus ik from here when you take the sum. That's okay. But this was in a plus 1, right? So e to the minus ik, right? Now I said that this is only for k bigger than 0, right? So I need to, by hand, put in the k smaller than 0. K smaller than 0 would be c minus k dagger, ck dagger, e to the ik, right? I had to take, because I'm only summing over positive k's, I need to explicitly put k to minus k to get the negative. But hang on a sec. C minus k ck looks awfully like ck c minus k, but they're opposite, right? So this thing is really minus ck dagger, c minus k dagger, right? And there's an emission conjugate that I can just write here now because this is easy to emission conjugate. Conjugate hermetically? I don't know. I don't know what the verb of that would be. So what we get is sum over k, ck dagger, c minus k dagger. Now check this out. E to the ik, e to the minus ik, minus e to the ik. Plus emission conjugate. Sine k, right? Sine k, when k equals 0, it's 0, as a p wave should be. Okay, so now I can go back. I can erase that, right? Or why don't I just go down here and draw on the floor? So can I erase this line and just rewrite it as compact line? Is that okay? So we get the ck bigger than 0, ck dagger, c minus k dagger, times I think there was a minus sign, and then 2i times sine k. I'm pretty sure those are the signs. Okay, now I can rewrite the Hamiltonian over here in the following way. So the Kitaya BDG Hamiltonian, I can write like this. ck dagger, c minus k. Now here, I need some 2 by 2 matrix. And on the other side, I'll write ck, c minus k dagger. And then, so to be proper, I should do this. It should be a row vector. so I don't offend anybody who's a mathematician in the audience. Right, so if I have a 2 by 2 matrix over here, I'll just get some sum of all the CKs. And what should it be? Okay, the CK dagger CK comes from the mu. That's just the tau z. Now there's another CK dagger CK comes from the J. Right? The hopping. And you know there's a half here, right? But that half combines with the t to the ik to the minus ik to give you a cosine. And it's a tau z. You all understand me when I write tau z? So tau z is the 1 minus 1 Pauli matrix, like sigma z, only with the tau. And then, oh, I didn't leave enough room. And then I have this guy. This guy connects this and that, and also this and that, right? And because it has an I in it, you're not surprised that it will show up with the tau y. And let me give it a different letter, delta, because in principle it could be different than the hopping. Sine k. This used to be equal j in this model, but it doesn't have to. It can be more general. And tau y is minus I and I in the off diagonals. Okay, this Hamiltonian is very easy to solve, right? And it's very easy to see where the topology in it is. This exhausted its usefulness, right? Do you agree? Anybody disagrees? So, you know, in principle, I have to be honest, I made a mistake here. This is not really BDG. This is just the Kitab model, right? I just rewrote it. This is the Kitab BDG. It's just the thing that's inside. Sorry about that. It's not a very big point, but I should make it. This you should just treat like a spin Hamiltonian. You can diagonalize it, right? You know that every momentum would have two states. Be the square root of the sum of this thing plus this thing. And if mu is positive, it looks like this. I think. What?
Why is mu in front of tau z? That seems like K and minus K have opposite chemical potential.
Ah, it's very nice. It's a good question. So this is something that comes in the BDG equation. Now I can show you this mathematically, and I can give you an intuition. So let me show it mathematically, because intuition is only good with some mathematical backing. So if you look at here, so you have CK dagger here, right? And it will multiply CK. So in the tau z, you pick up the 1, and that's what we want, right? But then there's another piece. Here should be a half overall, now that I explain it. But then there's this other piece, minus 1, right? Now check it out. It will be C minus K. It will be C minus K from here, right? Multiplying C minus K dagger. So it's CC dagger instead of C dagger C. So that's where the minus sign here comes in. And Right. And then the intuition is that this sector is the sector of particles, and this sector is the sector of holes. And you know, like with Cooper pairs, you can either create a particle or create a hole, and they give you similar things. So that's the intuition. And yeah. All right. But it's a very confusing thing. So this is a BDG thing. Now, anything that will come out without this tau z, well, should I say? Yeah, so you can deviate from this pattern when you have like spin-dependent physics, when you break time reversal. You can break this pattern. Okay, so this is the dispersion. When is it topological? When is it not topological? Do you know?
Just chart numbers.
Yeah, chair numbers. That's good.
Goes around once.
Goes around something. What? Actually, this can go around. Just you know, in your mind's eye, and on my blackboard, turn this into a z hat and turn this into a y hat. What is this thing? It's a vector. It's two-dimensional. It's great that it's two-dimensional because I can draw it on the board. So if I explore this, let's call it hy and hz, for obvious reasons.
Squared is missing. But
What?
Squared is missing.
Thank you. What shape is this vector going to make? Good? Ellipse, right? So let's see. So it will be centered around the y equals 0 from here. And then for k equals 0, it starts high or low, depending on how you want to think about it. And the 0 and pi mark k equals 0 and k equals pi. I drew a particular circle, but I could have drawn it like this. And I could have drawn it, if I had enough space, like this, which is topological. Come on, all these things, circle around, chair number. Here. It's obvious, right? It just goes around the origin. Right? So if you think about it as a spin, as a function of momentum, the spin will go full circle. Whereas if you think of the spin over here, it's mostly just pointing in the down z direction, right? It's mostly just a particle. Mostly just a hole. So tau z plus 1 would give you this negative, so mostly like a particle. But here, it mixes particles and holes as it goes around. And this is the topological. This is trivial. And what is this? Sorry? Gapless. Because the gap is just the distance of the origin to the curve. So the energy that I draw here is just the distance of the origin to the curve. This is a gapless point. Depending on mu, positive or negative, the gap would occur either at k equals, the gaplessness will occur either at k equals pi or at k equals 0. In this case, the way I drew it, it will occur in k equals pi, and the dispersion would look like this. So you go from a gap thing that looks like this to a gapless to a gapped. But there should be some mark left over due to the fact that this is topological. What's the mark? Majorana fermions, yes. So where the gap closes, you can think about an edge state that's left on the two edges. There's one state that stays stuck at 0. Y0 is the particle-hole symmetric point of the Hamiltonian. And I'll get back to that later. That's the Majorana. All right, this was Kitaev. Questions? Yeah, Shane.
So when you came up with the simple example, you got rid of a bunch of couplings, the mu and then the over.
Yeah.
So I see how the mu kind of comes back in by moving yourself into the trivial phase. But is there some competition between J and delta where you'll also lose where you kind of reconnect.
Yeah, that's a great question. And the answer here is no. The answer is no. So in the Kitaev model that I started with, J and delta were the same. You have 2 factors of 2 and stuff like that. I think they're the same.
Great.
They were the same. But I can deviate from that to say that the pairing is different. And it seems like as long as J can defeat mu, right? As long as there's a possibility for the circle to enclose the origin, it doesn't matter how thin or thick the ellipse is. Now I drew a circle, but it's actually an ellipse if delta and J are different, right? But there's a caveat. If delta is very small, delta will determine the gap someplace, right? So if delta is very small, you might end up with so if mu equals 0, for instance, right? Then you're at pi over 2. The gap will be determined by delta. So this corresponds to this situation, for instance. Right, if delta is very small, you can have a very small gap at some k between 0 and pi, and that means that if your temperature is not low enough, you'll just create a lot of quasi-particles. And you won't be able to see the parity of the Majorana separate from all the parities of the other quasi-particles that are running on the system. So from experimental perspective, it's important that this delta is large so that the gap everywhere remains large. And you don't have quasi-particles going around ruining your computer. I mean like the Microsoft topological quantum computer that will have in 3 years. And so we're talking tens of millikelvins here. Hundreds. So that's what's important in that. Other questions? Yeah.
Is the system at half filling? Like, do you find do you define the fermi level to be at 0, or can the filling be at any arbitrary?
So this is an experimental question.
Yeah.
Like you can kind of gate it, but it's also connected to a superconductor. So at first, there were 2 groups that came up with this proposal in terms of the quantum wires. So I was involved in one together with Felix von Oppen and Yuval Oreg, and the other one was the Maryland group with Roman Luchin and Shankar Dasarma and Jay Sao, I think. And people were debating whether this proposal is reasonable or not because they said, well, I mean, the wire is going to have some chemical potential somewhere. The superconductor is going to take that chemical potential and drag it through the roof, and God knows what will happen. But it turns out that these materials, the indium arsenide, neon, and timonite, has some magic property. I mean, we're lucky that the chemical potential sticks fairly close to some band bottom, and it allows us to see this. If we're optimistic and say that the Majorana interpretation is correct. But it didn't have to be. So mu, in some sense, is determined by an external gate plus the doping of the actual material, and there's a limit to how much the gate can pull, if I understand correctly. So yeah, the first critiques were, you're not going to be able to gate those wires. So it's a really good question. What's your name?
Savant.
Savan. Savan?
Yeah.
Thanks. Yeah, it's a really good question. So that, every term in this Hamiltonian comes with some caveats about whether the experiment can actually achieve it. Somehow it all set together. Other questions about Kitaev? All right, so what I want to do with this model is I'll show you that when we drive this model with a periodic modulation, we'll achieve this periodic modulation by, I erased the diagram, so I'll draw it again later, by putting another superconductor that's actually being modulated in time, or modulating the chemical potential in time. You can get a situation where not only do you have Majoranas here, but you have another Majorana appearing at half the frequency of the drive. And then the next thing that I'll show you is that, well, that's not actually restricted to a single drive. You can put a number of drives, you can beat the Hamiltonian up such that it oscillates with various frequencies. And each frequency has the potential of producing a non-equilibrium Majorana state. And that's what I mean by Majorana multiplexing. And it's very surprising actually that happens, because when you lose translational invariance, you expect that you just have a dense spectrum. And whatever edge states you have will just leak straight into the bulk. because the dynamics can couple the bulk and the edge. So that, by miracle, that turns out to be false. You can actually have multiple Majoranas at different frequencies, which means that a single wire can use time as an extra dimension for braiding. It's like, if you have a wire, you would think about it as a strictly one-dimensional system. But then once you start driving it, it's like you're producing extra wires. And you go from a chain from one wire, you go into a chain of several, and they can communicate with each other. So it becomes more of the geometry of a strip. So that's the thing that I wanted to show you with Kitaev. But if I have time, so I see I have another 15 minutes. Is that right?
Yes.
Right. Then I can also probably get to the other example of topology and drive coming together to give you nice things with this frequency pumping. So for that, I need to talk a little bit about the BHZ Hamiltonian. So again, Kitaev, it's really fascinating stuff. It's brilliant stuff by, a lot of brilliant people put a big effort into this, starting with Kitaev, ending with the experimentalists, me excluded. Yeah, I find this stuff very fascinating. So do ask questions, I love it. Anything? Satisfied? This is a simple model, but somebody had to write it. All right, so let's do you still have appetite for more? Can we do some BHZ? You okay? Or see Peter complaining over here, no? It's a smile of approval.
Go for it.
Okay. I was hoping for a break, but you didn't get my hint. So let's erase this and upgrade a one-dimensional topological model to 2 dimensions. Now, I'm not big on experimental motivation on that one. So the Bernard-Hughes-Zhang model gives you a very nice band structure that gives you a anomalous quantum Hall effect, I think, anomalous quantum Hall insulator, a Chern insulator. And it describes half of the degrees of freedom that actually occur in this experiments that Molenkamp has done on cadmium telluride, mercury telluride quantum wells. So just very quickly, if you have a mercury telluride mercury telluride cadmium telluride well, if the thicknesses of the cadmium telluride relative to the mercury telluride is sufficient, is just right, so not too thin, what ends up happening is that the semiconductor, which was boring in the middle, turns out to be a topological insulator with spin up electrons going one way and spin down electrons going the other way on the edge. And now, this came following a suggestion by this gentleman. And I guess Andre is faculty here still? You know, he's always in some superposition, so. And so this was really brilliant work. And it started with saying, well, let's just think about a Hamiltonian, but using spin-orbit coupling alone can give you this kind of physics. But it will only describe half the physics, so just one of the spins. And that would be an anomalous Hall insulator, if I remember my definitions right. All right, so let's write the Hamiltonian to describe an electron hopping.
With magnetism.
What?
You have to break time reversal symmetry.
Yeah, so this would be time reversal broken. So it would be half of it. Yeah. I have to admit that I was looking on Wikipedia this morning to make sure that I'm not confusing definitions too much. Okay, so here's the Hamiltonian. So you have electrons in 2 dimensions. Let's assume that it's a 2-dimensional lattice. We have hopping on the x direction, but we will be with a sign. Right, so e to the ikx moves you one side to the right, e to the minus ikx moves you one side to the left. It comes with a velocity. There's another velocity associated with moving up and down in the y direction. And then here's the time reversal symmetry breaking term. We also have a static field in the z direction. Comes from atomic origins typically, but this you can think of as a band gap. But then there's additional hopping that depends on the z direction spin. With cosines. Typically, in a band or in a semiconductor, you don't have this part. You just have two bands, right? So you can think about them as either up or down. But here you also have the pseudospin, or the spin gets mixed up because of the motion. So that's the spin-orbit coupling part. And this gives you the standard dispersion. Why is this topological? And I'm not going to say, how they came up with this. I think it's a very long story. Why is this thing topological? So this too can be written like Pauli matrices. This time not taus. It's not a superconductor, so we use sigma for the Pauli matrices. It's not a three-dimensional vector. Right? Okay. And now this three-dimensional vector is a function of two-dimensional momentum space. What can this three-dimensional vector do? So I'm going to explore drawing three-dimensional diagrams on the board, but I won't succeed very well. So in the second part of my lectures, I'll show you this in PowerPoint. But let's see how I get. So you have kx and ky in the dispersion, and sure enough, this thing gives you some paraboloid of a valence band and some paraboloid of a conduction band, right? And each point in momentum space has a direction of this vector d associated with it, right? So at k equals 0, it's in the z direction. But as we explore different k's, it moves sideways, right? And then it may move back to the up direction. It may move to the down direction, right? But think about it as like a candy wrapper. Each point on the candy wrapper, that's the Brillouin zone, kx and ky, has a direction associated with it, right? Now take this wrapper and ask, are those directions wrap around a what? Sphere. So this you can associate with the sphere and ask, where are all those directions pointing to? Right? And they can do something like this, or they can do something like this. Namely, as you explore this wrapper, things might move sideways, but then they'll move back up. This will be topological, this will not. And whether it's topological or not will tell you what's the whole conductivity of the system. So first of all, geometrically, if you want to ask, does this vector d in one of the, well, I guess the vector d is a vector d regardless of the bands, the spins will point along d or opposite to d, depending on which band you're in. But if you want to ask whether there's wrapping or not, you can do this following geometric trick. Just integrate over the following thing. This is this Pontryagin formula. Oops. Why am I writing it here? It's a triple product. Just ask, you have this direction n, which is d over its absolute value. And then you say, well, let's change kx by a little bit. It goes like this. let's change ky by a little bit. It goes like this, right? Okay, so if you take this, so this direction and cross them, it should be perpendicular to the sphere, right? To the unit sphere. So you dot with that direction. So this should give you the area that you cover on the sphere. Divide by 4 pi, and you get the number of times that you cover the circle. That's the Chern number. Now, you know, if we talk about a full band of electrons, then this will also give you the XY Hall conductivity. However, you know, we're going to have a system in which you have effectively a single particle moving in such a two-dimensional band. So it's important not to think of a full band, but rather to think about the dynamics of an individual particle moving in it. So we can actually get this from semi-classical dynamics of a single particle. So let's do it relatively quickly, and I'm happy to answer questions. There's a word that didn't appear yet in this lecture. Now, this is a lecture on topological systems. What is this part? What is that word that should start appearing? We didn't talk about bury anything yet. It has to be buried somewhere here. Bury has to be buried, I guess, somewhere in this lecture. So here it's coming to life. This formula actually reflects Berry curvature. So we can define, in analogy to a vector potential in real space, we can define the Berry connection So what do I mean here? Each state is marked with momentum k, right? And you can ask about the Berry phase, the Berry connection of that state as we change k a bit. And then we can define, so this, think about it as a vector potential. And when you take the curl of a vector potential, what do you get? What do you get when you take a curl of a vector potential? Magnetic field. Now, this is a vector potential in k space. So this is a magnetic field in k space. And on the one hand, we can write this formula as just this. Now, k is two-dimensional, right? So the curl of a two-dimensional will give you the third dimension. So let me just, to be honest, put a dot in the z direction here. And then this becomes a number. That number is integrates over the band to be 1 over 2 pi. And I won't go too much into the details of this, but I'm happy to separately or in notes. Okay, so we have this effective magnetic field. Now all we need to write is equations of motion. And with that, I'll stop. So what are my equations of motion? I have momentum change. What is the momentum change? Got it. Can I have this one? Yeah, it's true, 0 minutes. Momentum change, force, right? I need the h bar. But now, if you had a magnetic field, you would also add velocity cross magnetic field, right? Of h bar times e, maybe. Now, in complete analogy, you can say the RDT, what is it? You have a band curvature, right? So you need a group velocity, right? If you're in the lower band, then I'll put a minus because this is defined positive. But then there's something else that's completely analog to this, which is the velocity, but in momentum space, cross the magnetic field, right? But here's the geomagnetic field, the Berry curvature. Now the Berry curvature is in the z direction, so I'll put the z here and just write this. So it'll be perpendicular to the force, Hall, right? So if I want to write electric field, I'll write EE over h bar cross z times this thing. And I'll show you some graphics later of how this omega is distributed in momentum space in this diagram. And I'll even animate this motion. But for now, I just wanted to show you that this is an equivalent way for getting the sigma xy conductivity. If you had a full band of particles that are moving like this, and they were pushed by an electric field, how much current would we get? So first of all, if you average over momentum space and time, what would this be? 0. It'll always average to 0. Because even if you have a constant force, you move to various momenta, right? You always come back to yourself. So when you integrate, this will be 0. So when we averaged, so to 0. But this doesn't. And then if you want to write the density of electrons, here's your density of electrons, right? Multiplied by E, multiplied by R dot. Yeah, vector under the dot, multiplied by E, multiplied by R dot. That's the current, right? But then, on average, this becomes E squared over H bar, right? Times if I got all my 2 pi's correctly, then it should end up coming back to this. Coming back to this. But you know, time is up, so I won't check all the 2 pi's. I'll just let you do it. Okay, so what will I do with this? This space will become the space of photon numbers. This would be the direction of photons taken from one source. This would be the direction of photons taken from another source. And you'll see that the spin half that's being driven by 2 photon sources, by 2 lasers, will move in this N1 and 2 space such that it converts photons of one species to another. It will be universal. It will be independent of the frequency of the sources and their physics, etc. All right, quick questions? All right, think of some over lunch or later. And sorry for taking a few extra minutes.
Yeah, so we have a coffee break we'll reconvene here at 11.
11.